In this video lecture, we are going to explain how is the formation of liquid drop or liquid bubble, and with that we are going to find out the excess of pressure inside the liquid drop or the liquid bubbles. For that, what we will do, consider a spherical liquid drop. This is the spherical liquid drop. This is liquid inside drop. This is the liquid and air interface. Outside is air, inside is liquid. The liquid drop is spherical in shape because liquid has a property of surface tension, because of which it tries to contract its surface area, and out of all the possible surfaces with the same volume, the sphere has minimum surface area. Therefore, the free liquid acquires the shape of sphere and there will be a formation of liquid drop. This is like this one. Let us consider these are the molecules of liquids from all sides, and these molecules of a liquid exert cohesive force on each other, and because of that they tries to contract in surface area by bringing the molecules together, and because of that it will acquire a shape of a sphere. This is the concave side of the liquid. The pressure of the concave side of the liquid is more than that of the convex side of the liquid. Now, the outside pressure is the atmospheric pressure, and I will represent inside pressure as Pi, and outside pressure is Po. Pressure on the concave side is more, therefore obviously pressure inside is greater than pressure outside. The question is, how much is the excess of pressure inside the liquid drop? And for that we will derive an equation for the pressure, excess pressure inside the liquid drop. Let us consider we have to increase the size of the liquid drop. We have to increase the size of the liquid drop by increasing its radius from r to r plus delta r. The initial radius of the spherical drop is capital R, and the increase in the radius is delta R. Then increase in the surface area of this liquid drop is final area 4 pi in the bracket R plus delta R whole square minus initial area 4 pi R square. And it comes out to be equal to 4 pi in the bracket r square plus 2r delta r plus delta r square minus 4 pi r square. This is the increase of surface area of liquid. This 4 pi r square get cancelled. What remains is 8 pi r delta r. 4 into 2, 8 pi r delta r plus 4 pi delta r square. Here what we will see here is that since delta r is small as compared to the radius, delta r square is negligibly small. We ignore that. Here we will take this as delta r. We will ignore delta r. Delta r square as delta r is small as compared to the capital R radius. Then surface tension has a tendency to contract its surface area. In order to increase its surface area by this amount, 8 pi r delta r, in order to increase this much surface area, work has to be performed here. Therefore, work done to increase the surface area by dA is given by T into dA. This is one more relation that we have got already. Work done in terms of surface tension, relation between surface tension and surface energy. This much work done is required to increase the surface area by dA, and this much work done is stored in the form of energy, and that energy is the surface energy. Therefore, increase in surface energy, rather we will say increase in surface energy is equal to work done is equal to T into 8 pi r into delta r. This much is the work done. Now we will find out mechanically the work done to increase the area. How it can be find out? The work done to increase the area, I will write here, dW is equal to, it is the force into displacement. How much is the displacement? Delta R is the displacement. What actually force is? Force is pressure into area. How much is the excess pressure there to increase the area? Excess pressure to increase the area is Pi minus Po into area A into delta R. This comes out from pressure is equal to force upon area. Therefore, force is equal to pressure into area. Therefore, the force required to increase the area by delta R, this excess of pressure into area into delta R, and it comes out to be equal to Pi minus Po into area is 4 pi r square into delta R. This much is the work done to increase the radius by delta r, mechanical work done to increase the radius by delta r, and this much is the work done to increase delta r so as to increase the surface energy. This equation is in terms of surface tension, and this equation is in terms of the mechanical work. This much mechanical work is done to increase the surface area by this much. This much is the mechanical work to increase the surface energy by this much. Now, here work done is the increase in energy. Therefore, we will equate these two equations, and I will write these as T into 8 pi capital R 2 into 8 pi capital R into delta R is equal to Pi minus Po into 4 pi capital R square into delta R. Pi get cancelled. Delta R get cancelled. Here R get cancelled with square. Here 4 and here is 8, and hence I will write 2T is equal to Pi minus Po into capital R, and hence the excess of pressure inside the liquid drop Pi minus Po is equal to 2T divided by capital R. This is the excess of pressure inside the liquid drop and in terms of surface tension. More is the radius of the liquid drop, less is the excess of pressure. Less is the radius of liquid drop, more is the pressure difference inside the liquid and outside the liquid. आपल्याला माहिती आहे, आपण जेव्हा फुगा फुगवतो तेव्हा फुग्याच्या आतमध्ये हवा आहे, फुग्याच्या बाहेर हवा आहे. फुग्याच्या आतमधल्या हवेला आणि बाहेरच्या हवेला सेपरेट करण्यासाठी फुग्याची मेम्ब्रेन आहे. फुग्याच्या बाहेरली हवा ही ॲटमॉस्फेरिक प्रेशर आहे, जी कायम त्या फुग्याच्या मेम्ब्रेनवर कार्य करत असते. फुग्याच्या आतमध्ये आपण हवा भरली की आतलं प्रेशर वाढतं आणि फुग्याची साईज वाढते. फुग्याच्या आतमधली हवा आपण कमी केली की ॲटमॉस्फिअरचं प्रेशर त्या फुग्याला चारी बाजूनी प्रेशराइज करून त्याची साईज कमी करतं. फुगा फुगलेल्या अवस्थेत आहे कारण फुग्याच्या आतमधले असलेलं प्रेशर हे बाहेरल्या प्रेशरपेक्षा जास्त आहे. हे जसं खरं आहे तसं लिक्विड ड्रॉप साठी पण खरं आहे. लिक्विड ड्रॉपच्या आतमध्ये असलेली हवा, आतमध्ये असलेलं लिक्विडचं प्रेशर हे बाहेर असलेल्या प्रेशरपेक्षा, हवेच्या प्रेशरपेक्षा जास्त आहे. आणि ह्या प्रेशर मधला डिफरन्स हा त्याच्या रेडियस आणि सरफेस टेन्शनवर अवलंबून आहे. मित्रांनो, आपण लहानपणी सोप बबल तयार करतो. त्या सोप बबल मध्ये काय होतं, सोप बबलचा जो इंटरफेस आहे त्याच्या आतमध्ये पण हवा आहे, त्याच्या बाहेर पण हवा आहे. द इंटरफेस ऑफ सोप बबल or the membrane of soap bubble has Inside the bubble there is air, outside the bubble there is also air. Now this soap bubble has two surfaces in contact with air, and because of that the increase in area is, here we have to take twice of this one. If I take twice of this one here, you will get here 2 into 2 4, therefore excess of pressure inside the soap bubble is 4T divided by capital R. This is all about how is the excess of pressure inside the liquid drop and inside the soap bubbles. Thank you very much.